So, very welcome everyone to Prime Mathematics. Today we are going to discuss a very much beautiful theorem coming from linear algebra, which comes under your postgraduate, undergraduate level of exams. So, this is a very much basic theorem. It states that each elementary row operation has an inverse, and the elementary the inverse is also an elementary row operation of the same type. So, how we just look over. So, let's start the proof. So how is it done? Firstly, let us consider, or you can say consider a matrix A which belongs to Rn cross n tuple space such that, or you can say where A has a general entry given by Aij with the order m cross n. Okay. So if a elementary row operation has been applied, the first elementary row operation over the matrix A, we define this by a kind of property which is given by alpha times of A S J when I subscript is equals to S, and we have Aij as given by I not equal to S. So these are the basically operations that we multiply the sth row of that matrix by alpha, right? Similar manner, we have a second elementary row operation given by the property, which is it is Asj plus alpha dot Atj, and this property is given when I is equals to S, and it is simply Aij when I is not equals to S. Right? We multiply alpha with the thth row and add it to the sth row, we get this. And the similar manner, we have a elementary operation of a last, which is given by E3 over the matrix A, defined by the property AFJ when I is equals to T, ATJ when I is equals to S, and AIJ when neither of them means I is not equals to S, not equals to T. So the main statement which you need to prove that the elementary row operation, like if we apply E1 over the E1 prime of A. Now let me first define what is E1 prime, what is E2 prime, what is E3 prime. So let's define first. Suppose, or you can say let E1 prime A, E2 prime A, and E3 prime of A be the inverses, be the inverse elementary row operations, be the inverse elementary row operations of E1 of A, E2 of A, and E3 of A respectively. Right. So for granted, we have just considered E1 prime of A, E2 prime of A as the inverse elementary operation. So to show that this are the same type, we just use first the property like if we apply E1 over E1 prime of A to prove what you can say that we need to prove that E1 over E1 prime of A, or you can write it simply E1 over E1 prime of A, right, is equals to E1 prime over E1 of A, or one can also write as E1 prime over E1 over the matrix A. So how we do? Now first we're talking about LHS, or let's say we can consider here E1 prime of A is equals to, suppose I defined it as by Bij, or you can just define simply by considering an element from the matrix A. So one can write as even prime of A is the inverse, right? So inverse, as we used to do in even prime of A as alpha. So here it will be a reciprocal, means the inverse of alpha as a multiplicative inverse is given by 1 by alpha. So 1 by alpha of ASG when I is equals to S, right? And similar manner, if we write as Aij is as it is when I is not equals to S. Now, if we apply even, suppose we are considering this as a matrix B, right? Suppose we consider this matrix as B, right? Say, now what? If we apply even over even prime of A, it just simply means even over the matrix B. Even over the matrix B is just given by the elementary. You can say it is given by alpha times of Bsj when I is equals to S, and it is simply Bij when I is not equals to S. So now what further? We are interested to substitute the value of Bsj. Now Bsj means when I is equals to S. So when I is equals to S is given by alpha dot 1 by alpha dot Asj, right? When I is equals to S, and one can write as Aij when I is not equals to S. Right? So therefore, what we obtain? We obtain that Asj should be equal when I is equals to S, and Aij when I is not equals to S. If the elementary row operation done by even is same as the elementary row operation done by even prime of A, like that. So now we are going to apply the right hand side. Right hand side is what? Even prime over even of A. Now one can define even of A as with a property. We know that is alpha A S j when I is equals to S. It is Aij when I is not equals to S. So it will be even prime over the matrix. Suppose we consider this time as B. This time we consider this matrix as B prime, right? So this matrix is given by B prime, say, right? So if we apply even over B prime, so what we get? Now even prime is given by 1 by alpha dot Bsj when I is equals to S, and then we have Bij when I is not equals to S. So with this Bsj property is given by 1 by alpha Bsj is alpha times of Bsj when I is equals to S, and it is Aij when I equals to S, not equals to S. So alpha gets cancelled out. Now again we are getting the same expression in the above. So therefore now one can conclude that the elementary operation from even to even prime, or you can say if we take even prime to even, both are same. So thus it concludes that even over even prime of A is nothing but equivalent to even prime over even of A. Hence proved, right? And similar manner we can write similarly E3 over E3 prime of A is equals to E3 prime over E3 of A, and moreover E2 over E2 prime of A is equals to E2 prime over E2 of A, right? So therefore our statement has been proved that one can say that each elementary row operation has an inverse, means elementary operation we are talking about E1, E2 and E3 has an inverse which is called E1 prime, E2 prime and E3 prime, and the inverse is also an elementary operation of the same type like we just saw, right? Thank you so much. Because if we are talking about even to even prime to even, or we are talking about E2 to E2 prime, and E2 prime to E2 both are contributing to the same result. So therefore, our statement has been proved. Thank you so much. If you have any doubt, you can just comment in the comment section.